Welcome back, Chapter 2, Nuclear Fission, from the Walding textbook that follows the Queensland Year 11 and 12 Physics syllabus. Okay, there's a nice little cartoon there for you to start with, which is a little bit topical. So, fission's a term that's used in biology as well as in physics. Now, the meaning of it in biology, it's about cell division. In physics, we're talking about atoms dividing up in a nuclear reaction. Okay? So we won't worry about what the cells that gossip about other cells are on about. We're talking about the physics option here. So what are we doing today? We're going to talk about neutron-induced nuclear fission, picking up that one that we spoke about in 6.1. Come back to Einstein's mass energy equivalence, remember E equals mc squared, and have a look at fission chain reactions. So we're going to solve some problems and do some calculations before the end of this. So, when we talk about nuclear stability, we showed this graph before where all the atoms over this side of that yellow line will go through the decay to move that way, whereas the ones over this side of the yellow line will undergo nuclear fusion to head towards iron, which is our most stable atom in terms of binding energy per nucleon. It just means that the ones on the left lend themselves to fusion, the ones on the right lend themselves to fission. So this side's splitting apart, this side's joining them together. So neutron-induced nuclear fission. So a heavy atom, so something like uranium, plutonium, think of your classic radioactive atom, will split in two to form two nuclei. So what we've got here's our uranium, for example. We have a neutron that collides with it and it splits up, and in doing that we have these two guys come out the other side, but we also have three neutrons given off as well. And so the thing to remember here is what happens to those three neutrons given off. They've got to go somewhere, they've got to do something, and if this guy here can cause the fission to induce the fission, then these three over the other side here can do the same thing. And here's a result here, which is basically our chain reaction, where we have the first generation here and we have one atom that reacts. We have two daughter nuclei and with three neutrons given off, and let's assume that one's lost somewhere, and we have two other neutrons there and there, which can react with two uranium atoms and cause two to undergo. Then the next round you'll have four undergoing fission, splitting apart. So four atoms in this next one split apart. And if we keep going, this just gets exponentially bigger each time, and that's the result of the chain reaction. That's effectively an atomic bomb when we don't control it like that. And each step, each time there's that fission going on and the atoms are splitting apart, there's a heap of energy released, and that's the explosion of an atomic bomb. But we can use this in a nuclear reactor if we control it, and the important bit here is the control rods. So here's our reactor vessel over here on the left, inside this nice little containment vessel. The actual uranium reaction is going on in this chamber here. The control rods are there simply to absorb those extra neutrons that are given off. If we can absorb those neutrons given off, we control how quickly the uranium will decay. If we don't control it, then you end up with cases like Chernobyl, Fukushima, those sorts of things. And essentially this process is about, we have a heavy water in here, it is circulated through this other heat exchangers to transfer it to other water, turns a turbine here like we saw in earlier chapters. The heat becomes work, which in this case is becoming the electricity that we end up using. So on the left hand side there we have a bomb where it's totally uncontrolled and each neutron gets released to collide with another nucleus and the reaction keeps going. But in a power station, we have those control rods to absorb the extra neutrons as we go and control how quickly the reaction goes. Here's an example of the bombs that were used at the end of World War II that dropped on Japan. On our map over the corner there's Tokyo over in that little area there, and you can see where Hiroshima and Nagasaki were. This is the only 2 nuclear bombs ever used in any sort of wartime scenario. The rest of the bombs have all been tests. The top one there was called Little Boy, and that's a little picture of what he looks like. It's quite a large bomb, but essentially there's 2 charges in here. You can see in there's 2 radioactive sources there, and as it hits the ground, one of the conical one impacts into the one at the front there, and the impact of those 2 causes the uncontrolled chain reaction. This is different from Fat Man, which was dropped on Nagasaki, the second one that actually ended World War II, where you have a this round container, that's this orange container around the outside here of conventional explosives, to form a constant pressure wave on our radioactive source in the middle there, and it's under pressure from compressed from every angle at the same time, and it's timed perfectly to make the uncontrolled reaction go off. There's a bit different to the more modern ones, where we use sort of the fission primary explosive to set off a fusion reaction, which releases far more energy, and we need that first fission reaction to generate that 6,000 Kelvin of heat to get the actual fusion reaction going. Now, when we talk about this fission reaction, we're talking about an atom splitting apart, but it's important to understand that we obviously can't look at atoms, so we create a model of what we think is actually going on. So over at the left here, we have 1 neutron bombarding the uranium nucleus, and we sort of have this liquid drop model to show through the stages of how it splits up into 2 smaller atoms with different numbers of protons, and the 3 neutrons released there. So you can kind of imagine 2 water droplets sort of splitting apart, and that's kind of how we sort of envisage it. There's a nice little challenge question up the top there. It's also a nice little XKCD cartoon there. Go to their website, just Google it, you'll find it. There's some pretty good science cartoons for you. So mass energy equivalence is Einstein's famous equation, E equals mc squared. And if we think about what's written in the blue thing there, the blue cloud, what does the equation actually mean? The speed of light is essentially a constant, so if we ignore that, we have energy and mass pretty much being the same thing. And the change in mass is the change in energy, because mass and energy are effectively equivalent. They are like 2 different forms of the same thing. Think of matter as super compressed energy. So we used this formula a couple of chapters ago when we were looking at binding energies and things like that, and we're going to come back to it now. So 1 gram sample, which we convert to kilograms, is converted completely to energy. How much energy is produced? Every time we use energy, it's measured in joules because that's standard units. Write your formula down, chuck your numbers in, plug it into your calculator, and it all comes out in the wash. You get an answer. 1 by 10 to the negative 1 times 10 to the negative 3 kilograms times 3 by 10 to the 8 squared, the speed of light, 9 by 10 to the 13 joules. That's quite a lot. A bit more than like your kilojoules that you see on the side of your breakfast packet in the morning. Now, calculating energy using mass defect, there's 2 general ways that we go. We can either look at per atom of reactant, or we can look at per kilogram of reactant. You might like to pause the video and just jot these down, because this is your little ready guide as to how to solve these 2 different types of mass defects. When we're looking at per atom of reactant, here's our steps. Calculate the mass of reactants, the mass of your products, and work out your mass defect, which is delta M. That's usually in atomic mass units. Convert that to kilograms with our little conversion factor there, 1.66 by 10 to the negative 27. That is your mass in kilograms to plug into your mass energy equivalence equation, and it will give you your answer at the other end. Per kilogram of reactant, calculate the mass of one atom. So the mass number in atomic mass units, that's kind of like what we were doing in the first part over here, but we're doing that conversion back here at the start. Calculate the number of atoms of reactant present in 1 kilogram of reactant. So if we have the mass in atomic mass units, we convert that to kilograms, that is kilograms per atomic mass unit. If we just go 1 over that number, that will give us the number of atoms of reactant present. And then we calculate the total energy for 1 kilogram. Energy of one atom times the number of atoms. Let's have a look at some examples of that to clear them up. Before I go on, I do recommend the What If website. Here's a nice little one here about swimming in a pool of nuclear fuel. On the What If side of XKCD, he basically looks at some really out there sort of questions and analyzes it scientifically as far as you can to give you some pretty crazy results. Anyway, worked example 6.2b. Here's our equation at the top here. We have a neutron-induced nuclear fission because the uranium is being bombarded with a neutron. So, calculate the energy released joules per fission of one atom and joules per kilogram. So A is the first option that I had on the previous slide on the left, and B is the one on the right. So on this slide, we're just stepping through those processes that we had on the previous slide. That's why I suggested writing it down would be a great idea. Part A, we're calculating the joules per fission event. So calculate the sum of the masses of all the reactants and the masses of the products. And in this first bit here, we're doing the mass of the reactants. And if you're not sure about that stuff, you either get it from a table or you calculate it individually from each proton, neutron, and so on. So the mass of our reactants is this little bit here, which is the uranium atom plus the neutron. The mass of the products, which is there, and we have our two products here and the 3 neutrons given off, and notice everything we're doing here is in atomic mass units, or U. Add all of these ones up here and we get, here's our mass of the products. And instantly you can look at this and you can see what's going on. You can see from this that we've got our mass of reactants up here, we've got our mass of products. We want to calculate the mass defect, that's that bloke there, by subtracting the two of them. Subtract those two numbers, and this is what we're doing down the bottom here. Simply subtract the 235.8 etc. from the 236.05 and so on, and the mass defect is 0.192452 atomic mass units. Next step, convert that to kilograms, because we're going to head towards E equals mc squared, and m in E equals mc squared, the mass standard units are kilograms, so we multiply by our conversion factor 1.66 etc. and get a mass defect of that tiny amount of kilograms. That goes into E equals mc squared to convert it into energy, which is in joules. Okay, we've done that before in earlier chapters, so that should be relatively straightforward. Now we've got to look at the next one, joules per kilogram. So that's the right hand side of the previous guide that told you how to work these out. So calculate the mass of one atom of reactant in kilograms. Okay, mass number in U times that conversion factor. So this is reactant, so here's my reactant here, get that from a data table, etc. Times the conversion factor this is the mass of reactants in kilograms. I should note on that screen there, it's actually the minus 25. There's a little typo on the screen there. We know that because that number appears just down here when we calculate the atoms, the number of atoms of uranium-235 in a kilo. Do the 1 over fraction thing that I showed you before, 2.56 pi 10 to the 24 atoms, just a couple. And then you want the total energy for 1 kilo of reactant. So that number there comes down here. All right. Energy released from that many atoms is that number there, times our little number there, the other one, gives us this figure down the bottom here, 7.38 by 10 to the 13 joules per kilogram. Okay, it's worth pausing and looking at those numbers, because I've gone over it very quick, just to see where the numbers come from each time. There's a little challenge there, challenge 6.2b, I encourage you to have a look at. I also encourage you to have a look at this XKCD poster, which gives you an idea about radiation doses. Okay, and we start with the blue ones there, which and everything in that blue square there is a little bit on the green one, and so on, and it keeps working its way up. And if you go to that website, you can zoom in and read all those different figures there. Alright, so what we've done, we've looked at the neutron-induced fission reaction. We did that one. We came across mass energy equivalence again. We had a look at the chain reactions, how those neutrons were released. Every time a neutron hits a uranium atom, 3 more are released, which can hit another 3 atoms, and so on, and it keeps cascading there, bigger and bigger. And we had a look at our calculations in those last couple of slides. I do recommend you go back and look over them again, just to make sure you've got the numbers right. Alright, that brings us to the end of today's lesson. Have a look at the Check Your Learning 6.2, it's on page 195, and once again, have a look at chapter 6.3 so you know what's coming. Okay, thank you.